Great. So hi, everybody. My name is Emily Stevenson. I'm a current master's student at the University of Exeter. And today I'd like to talk to you about microplastics and antimicrobial resistance, or AMR. So both microplastics and antimicrobial resistance in the environment are significant global threats. Microplastics, by definition, are any plastics less than 5 millimeters in size, and antimicrobial resistance involves microorganisms able to survive and reproduce in the presence of antimicrobials. So to understand how microplastics and antimicrobials or antimicrobial resistant organisms may interact in the environment, it's important to understand how they both get into the environment and into the aquatic systems in particular. So microplastics, there are lots of different sources of these getting into these systems. And when we look at the sources of antimicrobials, they very much overlap with the sources of microplastics. So there are many instances where antimicrobials and microplastics may overlap in the environment and coexist. Now, when microplastics get into the environment, they become colonized by microorganisms, and this creates biofilms. So for my research project during my master's degree, myself and my supervisors, as you can see on the screen there, wanted to look at whether different microplastics were differently colonized by E. coli. And we were particularly focusing on virulence, so pathogeneity, so disease-causing organisms, or antimicrobial resistant strains. So to be able to do this, we took 3 different types of microplastics. We incubated them in sewage, ensuring that they were sterile beforehand. And then we were able to enumerate the E. coli that were present on the microplastic surfaces, both resistant and non-resistant. And then using molecular tools, we were able to identify if they're potentially pathogenic or not. So what did we find? Looking first at pathogeneity, so here you can see the 3 microplastics, and then the red bugs are pathogens, so disease-causing organisms, and the blue are non-pathogens or commensals. And what we found was not only were pathogens enriched on microplastics, but different microplastics were differently enriched by pathogens. And now looking at antimicrobial resistance, so this is shown by the yellow dots, what we found was that actually the bacteria surrounding the microplastics in the liquid phase were actually more antimicrobial resistant strains than the ones on the microplastics, but pathogens on the microplastics were more likely to be resistant than none. But this was not significant, so requires further testing. We also found through research that microplastics may directly drive antimicrobial resistance, the evolution of this, by adding selection pressure of antimicrobials. Whether this is antimicrobials in the microplastics or sorbed to the surface, or just due to the closer proximity of individuals in biofilms. So what we found is that potentially microplastics could be hotspots for pathogens and antimicrobial resistance. Now we know microplastics have the ability to disseminate these attached microorganisms to perhaps pristine or non-native environments or between trophic levels. And this requires further testing. So thank you for asking me to speak today. Thank you to my supervisors, and I welcome any questions.